Okay, great. Our next speaker is Lise Ramambason from Heidelberg University, and she's going to talk about a lifetime of atomic and molecular clouds.
All right. Thanks for the organizer for giving me the chance to present this topic. I'm going to talk about timescale in the molecular gas and the atomic gas. And specifically, I will try to give you an overview of the different methods to measure timescale from observation, which are static, so reconstruction method, and to give you a highlight of the key results that have been obtained before the launch of JWST, and new observations providing a very detailed view of the multi-phase and multi-scale structure of the interstellar medium. So this work has been, the works that I will present are mostly carried out as part of the PHANGS collaboration with my main collaborator listed here. And specifically, I will highlight a lot of work from Melanie Chevens and J.M. King in Stanford University. Yes. So the context of this talk is going to be the measurement of timescale. But why do we want to measure timescale? The idea is that if you have a precise measurement of the time it takes to form stars within molecular cloud, then you can get some insights on the physical mechanisms that are driving this evolution of clouds and the formation of stars within them. So if we look at the view of an entire galaxy seen at a very high resolution, you can see already that the structure is linked to some multi-scale processes, and these physical processes are acting on different physical timescales. So the idea here is to reverse the process to measure the timescale in order to put some constraint on the physical processes that are initiating star formation, but also regulating it as the molecular clouds are evolving. Because this talk is supposed to be from the atomic to the molecular gas, I will start from the cold atomic gas cloud and then discuss a little bit what we know on the formation of giant molecular clouds with scales around a few hundred parsecs, and then how stars form within these molecular clouds, and eventually how the feedback from the stars that are formed within molecular cloud is going to act on their host molecular cloud and eventually disrupt the clouds. So these clouds are not isolated entities, and if we want to understand this cycle of matter, ideally we would like to probe this cycle in a variety of environments. And in the nearby universe, we have access to a lot of different galaxies. Sorry. From early type galaxies, like elliptical, to gas-rich later type galaxies that come in a whole lot of different morphologies, some of them having clear spiral arms patterns and others being more flocculent or irregular galaxies. Another interesting proxy that we can look at is also the influence of the stellar mass, specifically because there's the link between the stellar mass and the metallicity content of the galaxies. So in the nearby universe, we also heard from previous talk that you can access actually galaxies that have a smaller stellar mass, like the LMC or some other dwarf galaxies, and that in this galaxy you actually probe a regime that is chemically different with less dust and less heavy elements, which is going to change this molecular cloud cycle. So just as a context, this is the view of the different components that you find in a typical galaxy. Here I picked a late type galaxy, and you can see the surface density profile as a function of radius for the main component of this galaxy, the stars, but also the gas reservoir that are fueling the star formation. So you have the total gas reservoir in red, which is composed of the atomic and the molecular gas. And what is interesting here already, and I will come back to that when I speak a bit more about the JWST results, is that the dust is actually an excellent proxy to probe the total gas mass if the dust is well mixed within the gas reservoirs. So the right plot is showing the same kind of profile for an elliptical galaxies where the stars have almost fully consumed the gas reservoirs. And the idea is going to understand a bit more this interaction between the cold gas reservoir and how it collapsed to form stars, but also the reverse arrow, how the stars newly formed are impacting the gas reservoirs. Okay, so as I said, most of the results that I'm going to present take advantage of the PHANGS survey, which is a multi-wavelength survey targeting a few, almost 100 of galaxies in the nearby universe within 25 megaparsec. And the great strength of this survey is that it is multi-wavelength. So as you can see, you can access all the different components that I highlighted before. With ALMA, you can probe the molecular gas, assuming some conversion of CO into H2. With VLA observation, you can probe the atomic phase at a somewhat lower resolution. JWST is providing a view of the dust component, and you have access to a variety of tracers of recent star formation from the mid-infrared up to the UV. So this multi-wavelength aspect is really critical to probe the multi-phase structure of the interstellar medium. And a second key aspect is the spatial resolution that is accessed almost cloud scale for most of the sample. I will present a few methods to measure timescale and highlight why this resolution is critical for timescale measurement. Okay, so diving in the timescale subject, what are the timescales that we can measure? The easiest one, and we've heard a little bit already in the previous talk about it, is the depletion timescale. So for example, here, I'm showing the Koenig-Schmidt molecular Koenig-Schmidt relation, showing you the surface density of star formation rate as a function of the surface density of molecular gas. And most of the galaxies are lying on a single linear line corresponding to a timescale of only 1 to 2 megayear. And this timescale is actually extremely stable over a variety of environments and also over redshift. So if we could convert the entire mass of a galaxy into stars, this is the timescale that would be associated with it. But a surprising fact is that if you look at the theory for self-gravitating molecular clouds, the timescale of a free fall for such a molecular cloud is much smaller, closer to only 10 megayear. So there is a tension between the timescale that you would expect at small scale if the gas is collapsing without any support, and the timescale of entire galaxy that is indicating that in galaxies, the star formation is actually extremely inefficient. So most of the gas is sitting there, but is not actually collapsing and forming stars directly. Okay, however, molecular clouds are not free-falling. There are some mechanisms like turbulence or other physical mechanisms that can support the molecular clouds and prevent their collapse in such small time. So the idea of the method that I'm going to present in the next slide is to have some measurement without assuming any physics, just from the cloud distribution that is observed at high resolution. So how can we measure the lifetime of molecular clouds in galaxies? The idea in all the methods that I chose to present is to look at the relative distribution between gas tracers and stellar tracer and assume that, of course, you're looking at a static observation, but because you observe enough region, you can capture molecular clouds in different phases of their evolution and infer a timescale based on the number of clouds that you capture in each phase. So the first method that was developed is based on the cloud classification, classifying clouds that are actually forming stars and clouds that are inert and counting them. Another interesting method is to look at cross-correlation function. So this metric provides a measurement of the clustering of different populations. So here, for example, we're looking, this paper are looking at the clustering between a catalog of giant molecular clouds and a catalog of clusters, and see how they correlate in space. And other method, I've also used the dynamics of galaxies and the fact that if you know precisely the gas flow in between spiral arms, you can track molecular clouds that are formed in the spiral arms and survive in the inter-arm region and derive some timescale based on this survival of clouds. But I'm going to present a third method that is slightly different, which is, again, coming back to this Kennigan-Schmidt relation, but using very interesting properties, which is that this relation breaks down. So I've told you previously that this relation is holding for many environments at different scales, but when we look at cloud scale, this relation is actually breaking down. And the reason for that is that the position on the Kennigan-Schmidt plot that I'm showing here is going to depend on the phase of the evolution of molecular cloud in which the cloud is captured. To illustrate this, if we capture a molecular cloud, which is in this phase, before the star formation is starting, well, you're only measuring some molecular gas emission, but no star formation rate tracer. So the molecular cloud is going to appear below the Kennigan-Schmidt relation. On the other end, if you capture a molecular cloud that is at the end of its life, you're mostly capturing the emission from the stars, but the molecular cloud is already destroyed. So you have a positive bias. You measure a star formation rate, which appears to be higher compared to the molecular cloud. And the idea of the method that I've been using and that we've been using in my group is to quantify this decorrelation, this deviation from the Schmidt-Kennigan law with what we call the tuning fork method. So the idea is to use two maps and their spatial distribution, one map of the gas, for example, ALMA, and one map of the stars, for example, here, I think MUSE, and to identify the peak of emission and to measure the gas to stellar flux ratio. So it's a flux weighted method as a function of different aperture size. And the idea is that at small scale, if you focus on gas peak or on stellar peak, you will see this bias that I was presenting earlier. But when you increase the aperture size, you slowly converge towards the galactic average, which is lying on the Kennigan-Schmidt relation. So this characteristic shape can be fitted with a complex model, which depend only on quantities that are directly measurable on the maps, like flux fraction or contrast parameters, and of three independent parameters that are controlling the asymmetry of this fork and the amplitude of this fork and the inflection point. As a function of these three parameters, the T-gas, the gas timescale, T-over, which is the time of overlap between the two tracers, which can be considered as the feedback timescale, and lambda, which is a spatial parameter at which the two tracers of gas and star are decorrelated. Okay. So this method has been applied extensively in the local universe to measure the lifetime of clouds and the duration of feedback. But it has also been applied in simulation as a metric that could be interesting to probe the feedback recipes, with the idea that in the simulation, because this decorrelation at small scale is observed in the nearby universe in every galaxy, the simulation should also be able to reproduce this decorrelation at small scales, which is only the case for some specific feedback recipe. So it's been a very complex and degenerated problem, but it's an interesting metric that has been used also to connect observations and simulations. And I will now present the few results obtained in the nearby universe, and specifically applying this methodology to the PHANGS sample, using as a tracer of the gas the ALMA emission that is obtained for galaxies coming with a wide range of morphology, and for the tracer of the star formation rate, the H-alpha emission with ground-based telescope and MUSE, and also taking advantage of the recent JWST observation, providing a mid-infrared view of the star formation. So the first key result that was obtained is on the cloud lifetime themselves. The first paper that came out on CO emission measured the cloud lifetime for a sample of 54 galaxies in the KIM 2022 paper. And they found that molecular clouds are actually transient objects with a short lifetime of only a few times their freefall time, so 10 to 30 megayear only, hinting at a rapid cycling of molecular cloud and rapid disruption by stellar feedback. They also showed that this timescale is environmentally dependent. So depending on properties that are global integrated properties of galaxy, you will have typical molecular cloud living for different lifetime. And the star formation efficiency that are measured based on this timescale measurement are actually also quite low, because as I was saying, we are very close to the freefall time, only a few times higher. The star formation efficiency measured were of the order of 1 to 8%. A second very interesting result concerned the feedback phase, and specifically, we added just a piece of evidence, an interesting result with a PhD students working in my group when we focused on the cloud lifetime in inter-arm regions and spiral arm regions, with the idea that maybe in spiral arm region we would have expected a shorter lifetime because of shear or collision of just the dynamic of spiral arms, but actually except for an increased surface density in the spiral arms, we could not find a significant difference of the cloud lifetime and the star formation efficiency between arms and spiral arms. So it was a recent result by Andrea Romanelli. We also showed in the second, in the same KIM 2022 paper, they focused on the feedback phase traced by the overlap of CO and H-alpha. And what they found measuring this timescale is shown here on this little histogram, is that the feedback timescale is of the order of a few megayears only, with a median at 3 megayear. And this was a strong indication of pre-supernova feedback driving the description of molecular clouds, with the idea that photoionization and stellar winds are acting on timescales that are short enough to disrupt the molecular clouds, and that supernovae that explode around 4 megayear for the first supernovae could have an impact, but only after a first pre-processing of the molecular clouds by pre-supernova feedback. So this was a very interesting result, but one phase that was missing at the time is the embedded phase of star formation, on which I spent a large part of my work. And specifically taking advantage of the fact that since recently there's been this amazing addition to the PHANGS sample, which is the mid-infrared view covering 74 galaxies in 8 photometric bands. And the 21 micron band has been shown to be an excellent tracer of the embedded star formation, where you cannot detect the star formation in the optical, but it can be traced in the mid-infrared. So, yes. So in my recent paper, we focused on measuring this embedded phase, and specifically, we compared the result, the timescale that we obtained for feedback when we include this embedded phase of star formation, and we plotted it against the exposed phase of star formation that is visible in the optical. And what we found is actually that most galaxies lie on a 1-1 relation, and the obscure phase of star formation was found to be very short, less than 4 megayear for all the galaxies in our sample, but even consistent with just being smaller than 1 megayear. So this very short obscure timescale is consistent with ages obtained from SED fitting from stellar cluster. So it seems that this phase is actually absent, almost absent from most galaxies in our sample, with the exception of a few galaxies here. We found that actually there could be an impact of the morphology of the galaxy, because the only galaxy where we do detect an obscure star formation phase are the barred spiral galaxies in our sample, which are also the most metal-rich galaxy in the sample. So in that sense, there could be a combined effect of both the morphology, the presence of a bar, for example, and also potentially of the metallicity of this galaxy, with the idea that at low metallicity, there's numerous changes in the structure of the interstellar medium. And for example, the increased escape of ionizing photon at low metallicity could be linked to a faster disruption of the molecular cloud. So this is still to be connected quantitatively, but it's ongoing work right now. So this is my part one summary. We've been able with this method to put some timescale on the different phases of the molecular clouds. And there are many projects that are coming up after. The project is to focus on different tracer of the dense gas. For example, there's a student working with Lucas Neumann at ISO, focusing on the application of this method with HCN. There's also applications coming up on galaxies that are undergoing complex interaction, for example, interacting galaxies like the antenna. And the idea, one idea would also be to explore a bit more the low metallicity regime, where there might be some difference in the timescale, with a survey, a PHANGS dwarf survey that is going to extend a bit the metallicity range probed in PHANGS. So in the few minutes that I have left, I will add a few words on the timescale of atomic gas. And the reason why I spend less time on it is because we don't have many measurements. And one problem for this is the resolution of the observation in H1, which have currently enabled only a single measurement in the Magellanic Clouds, where in Ward papers, they measured a timescale of around 48 megayears, so longer than the molecular cloud, compatible with a model where this timescale would be regulated by the collapse of the mid-plane through gravitational forces. And with a PhD in my group, we're working on connecting this timescale in the LMC with a very detailed view that is now obtained with the local volume mapper survey for the different ionized gas properties resolved in each of these little hexagons. And of course, there are also possibilities for future measurements. There's already part of the sample that has been covered by Cosima Eibensteiner at higher resolution with MeerKAT. And with the SKA, there's the hope that for many more galaxies, we could also add this little piece of information on the atomic timescale. But meanwhile, our best try to concern the timescale of the neutral gas is actually to use the polycyclic aromatic carbon as a proxy of the high resolution ISM and of the dust that is mixed in the gas. So this idea comes from an empirical correlation between the CO measurements and some of the dust bands that are tracing this emission of paths, for example, the 7.7 band. So in a recent paper, we measured the timescale associated with the different photometric band available in the JWST. And we found that the PAH clouds that are traced by this band are actually surviving on timescale very similar to the CO clouds. So once you have PAHs, they provide shielding that is sufficient to allow the formation of CO on timescales that are really short. There are exceptions. So the one-to-one relation would be what we expect from this correlation that I was showing earlier. But you can see that the only two low metallicity galaxies in the sample are actually offset of this relation. And this could be linked to the presence of CO dark gas, which is not detected in CO, but is shining in the 7.7 band. And There's also a few of outliers of this relation below, with a deficit of PAH compared to the CO emission. And these are actually very specific regions that have been studied in J.M. King paper 2026. And she also recently obtained some JWST spectroscopy to investigate the mechanism responsible for this apparent PA deficit. And now I'm reaching my part 2 conclusion. We added a little part, mostly focusing on the PA emission before molecular clouds form. And there are, for now, not so many measurements of the atomic H1, but this could come with the arrival of the SKA. And there's also, on the other side, efforts to connect this average timescale to the H2 region properties. So these are the few prospects for this field. First, there's still some work to build really high-resolution catalog of PAH clouds. This is ongoing work, and also in parallel works to calibrate this large photometric band with JWST spectroscopy. And to connect the clouds to the H2 region properties, there's different ways to do that, but you will hear a bit more about approaches with multigris, for example, to measure the ionized gas properties in the talk coming just after me. Thank you very much.
Thanks, Lise, for a nice talk. Time for questions.
Thank you very much. It's a very nice talk. I have a question about the pH property in the same 0.7 micrometers. Do you also consider the contribution of the different pH charge state, for example, pH like a cation and the anions or neutral pH contribution on that band to support CO dark gas stressors?
We don't. So here, that I think this could be something linking to my second bullet, but because now we're just using the spatial distribution of the entire band. So there is already some work going on to disentangle the continuum from the pH emission, because just using the spatial distribution is not actually enough to really understand the physical mechanism powering this band. So I guess the charge, to my knowledge, this it's not been done, but this could be something done with the comparison with spectroscopy, actual spectroscopy, and not just photometric band.
Thank you.
Hi. In this analysis, in a way, it relies on thinking that everything is a unit with a border, right? So what happens if you have an H1 conversion to CO cloud while you have star formation? How does the analysis changes if the cloud is not a unit with boundaries, but it's still being fed?
Yeah. So that's one of the challenges of this timescale measurement, not only this method, but all the previous one that I presented. And this method was initially developed because this flux weighted that we are using, we're considering like the flux ratio as a function of different aperture size. So we don't really have to define clearly the boundaries of the cloud, like you would do, for example, for cloud identification, where you need an algorithm to extract the structure with a fixed size or a fixed threshold. Here it's a flux weighted, and this shape is not dependent on a specific size. So this is, I would say, like solving a little bit this identification problem. But what we are not solving at all is the idea of that we assume a sequential star formation. So if there are reaccretion or something a bit more complex than this very schematic timescale that I showed, we cannot really account for it. This is also an average view of a typical molecular cloud for an entire galaxy. So it's only representative of like the molecular clouds that dominate the emission, not of any outliers that could be there in specific region of the galaxies. Yeah.
We have time for one quick question.
Thank you. From the galactic point of view, your inner molecular phase there is, you say 20 to 30 million years, and the obscure star formation is about 4 million years. So you will expect to find basically 10 times more clouds without a star formation than with any formation. But when you look at clouds in our galaxy, every time we look at a molecular cloud, there is a star formation. So how do you combine those two contradictions?
That's a good question. I don't know how we combine this. This is slightly different from just the result that you could get by identifying clouds. So this flux-weighted measurement, they also take into account any peak of emission that is going to be associated, like any peak of emission that is compact enough, because what we do, and that I did not mention, there's also a filtering part where we remove the diffuse emission, but any compact emission is going to be associated with this first phase. So maybe it could be that this is a different way of identifying clouds, and that just in the galaxy, there's no CO emission that is just alone sitting there without any other counterparts. It could also be, I guess, some sensitivity issues, because here our methodology also relied on the idea that for any phase of the cloud, we can detect it in any of the tracer that we would like. But if there are some mismatch in terms of sensitivity, this could bias the duration of the isolated phase where you only see one of the tracer and not the others. So I don't have a very convincing answers, but I guess these two avenues could be explanation for these differences. Yeah.
I mean, it's not just specific to your work. It's like, I mean, I'm a galactic astronomer, and when I go to extragalactic meetings, I see these times, and kind of like, I think we have a problem there.